Hello dear learners, welcome back to my YouTube channel. So today in this video we will be discussing the application of the Gauss's law. So we will do one derivation and the topic of the derivation is to find electric field at any point due to a long line of charge. So we will do this derivation, which is an important derivation for class 12th. So let's start the derivation. So what we will consider is, we will consider a conductor, a wire, okay, and we will give some charge to that conductor. So when the charge is given to that conductor, the charge gets uniformly distributed throughout the length of that conductor, and hence we will get a line of charge. And because of that line of charge, we will find out electric field at any point using the Gauss's law. So let's start the derivation. So here we are taking a long conductor, let's say AB. So this is our conductor. Now in this conductor, when we give charge, let's say Q, we are giving charge Q to this conductor, then that charge gets uniformly distributed, and we are giving positive charge here. So this charge gets uniformly distributed throughout the length of this conductor. So as this charge gets uniformly distributed through the conductor, we will get a line of charge. And because of this line of charge, at any point, we are going to find out the electric field. And for that, we will be using the Gauss's law. So let's say that we are finding the electric field at any point P. And this point P, let's say, is at a distance of R from the conductor or from the line charge. So we are finding electric field at this point P due to this line of charge. Now before we apply the Gauss's law, what we need is a Gaussian surface. So a Gaussian surface is an imaginary surface which encloses the charge, which covers the charge. So here, since we have a line of charge, so we will draw a Gaussian surface which will be cylindrical in shape. And we will say, or we will consider that the Gaussian surface exactly passes through the point P, so that the radius of the cylinder will become R itself. So let's draw the Gaussian surface here. So as I said, the Gaussian surface will have the radius as R. That means the cylinder, it will exactly pass through this point P. So here you can draw the Gaussian surface, which will be a cylindrical set, and let L be the length of this Gaussian surface, right? So here you can see the radius of the Gaussian surface will be exactly equals to R, so that the Gaussian surface passes through the point P here. Now let us say that the charge density here means charge per unit length. So charge density on this conductor AB is given by lambda. So lambda, which is our charge density, will be equal to charge divided by the length. So charge density is charge per unit length. Its unit will be coulomb per meter. So while doing the numericals, you have to know the unit. So charge density is nothing, charge per unit length, in our case where we are finding electric field due to a line charge. Alright, so if you cross multiply, then here you will get charge will be lambda times L. So let this be our equation number 1. So what we have done, we have given charge Q to this length of the wire or the conductor, and what we have calculated is charge density, which is charge per unit length. So the length here is L. So what is the charge present in unit length? That is our charge density. So lambda is Q divided by L. You cross multiply, you will get total charge Q is equals to lambda times L. So this is our equation number 1. Now as we are using the Gauss's law, so we have now the Gauss's law. It says that integration of S E dot ds is equals to Q divided by epsilon naught. So integration S, this circle here you can see it represents integration over the entire closed surface. So this Gaussian surface that we have, this is the Gaussian surface that we have drawn, which is a cylinder. So this Gaussian surface has three surfaces: the top surface, bottom surface, and the curved surface. So this closed integration means integration over the entire surface of the Gaussian surface. So integration S E dot ds is equals to Q divided by epsilon naught. So this we get from the Gauss's law. Now we already have the value of Q. So let's put the value of Q here. So integration of S E dot ds will be equal to, instead of Q we can write down lambda L. So it will become lambda L divided by epsilon naught, and here we have used equation number 1. So what we have done, we have found out the total charge Q, and then we have used Gauss's law and we have replaced Q is equals to lambda L from equation number 1. Now as I said, this integration is a closed curve integration over the entire surface, and since the Gaussian surface that we have is a cylinder, it has three surfaces: top, bottom, and the curved surface. So we will split this integration into three different parts. That is integration for the top surface, integration for the bottom surface, and integration for the curved surface. So let's split this closed curve integration into its components. So now what we are doing is we are splitting this integration S E dot ds into three parts, as the Gaussian surface has the three surfaces. So the first one is the top surface, so like we can write it here as top surface, so E dot ds. Then it has the bottom surface, so we can write down integration bottom E dot ds. And the third surface it has is our curved surface. So we are integrating E dot ds over the top surface, bottom surface, and the curved surface. So when we add all these three, it becomes a closed surface here. So I hope this is clear. We are splitting this closed integration into three components, which is top, bottom, and curved. So for each top, bottom, and curved, we need to find the value of E dot ds, where E here is the electric field and ds is the area vector. So let this be our equation number 3. So our intention here is to find out the value of the electric field. So for that, so let's first find out the value of E dot ds for the top, bottom, and the curved surfaces, right? So let's do it for the top surface. So for top surface, let's see the value of E dot ds here. So for top surface, E dot ds can be written as, since this is in the form of A vector dot B vector, and we know that A vector dot B vector is nothing but AB cos theta. So here E dot ds can also be written as E ds cos of theta. So we will write this as E ds cos of theta. So why we are writing this is because we know in vector A vector dot B vector is our AB cos of theta. So similarly, E vector dot ds vector can be written as E ds cos of theta. So let's find out the value of this theta for the top surface. So for that, what we will do is we will consider a small area here. Let this area be ds. Now we know that the area vector, area is a scalar quantity. So when we represent it in a vector form, then what we do is we draw an arrow perpendicular to that area. So this arrow gives us the area vector ds. So it has the direction, it is going perpendicular to that surface area ds, and the length of the arrow will give its magnitude. So this arrow here going upwards perpendicular to this area ds is called as the area vector. So this ds is going upwards. Now what kind of charge we have given on this conductor? We have given positive charge, and positive charge, the electric field always goes away. So the direction of the electric field here will be this side. That means going away from the charge. So E will be directed this side. Right? Now, theta is the angle between E and ds. Here, theta is the angle between A and B. Similarly, here, theta is the angle between E and ds. Now, look at this. E is going towards right, ds is going upwards. So, the angle here between E and ds will be equal to 90 degrees. So, here, the value of theta will be equal to, so E dot ds on the left hand side. On the right hand side, we have E ds cos of 90 degree. Since from the figure or diagram, we have seen that theta will be equal to 90 degree. I hope this is understood. So theta equals to 90 degree here. Now what is the value of cos 90 degree? The value of cos 90 degree is zero. So the value of cos 90 degree is 0. That's what we are using here. So since cos of 90 degree is equals to 0. Now 0 multiplied with anything gives us 0. So this becomes E dot ds equals to 0. Let this be equation number 4. So we have found out the value of E dot ds for the top surface and it comes out to be 0. Now similarly we need to find out the value for E dot ds for the bottom surface and the curved surface. So let's find out that. So similarly for bottom surface, we can write E dot ds is equals to E ds cos of theta, or E dot ds is equals to E ds cos. Now again we need to find the value of this theta. So we are talking about this bottom surface. So we will follow the same process again. We will consider small area ds here. So this is area ds. So its vector area will be perpendicular to that surface. So this will give us area vector ds. And again, since we have given positive charge, the direction of the electric field will be away from the charge. So it will be in this direction. I hope this is understood because I have already explained it here, how we are getting those things. So the value of theta here is also 90 degrees. So area vector is always drawn perpendicular to that surface. So we are considering the bottom surface. So that's why area vector ds is going downwards, perpendicular to the surface. That is the bottom surface. And since we have positive charge here, electric field will be going away from the charge. So here angle between ds and E will also be 90 degree. So that's what we will replace it here. So this also becomes cos of 90 degree. Here you can write since theta is equals to 90 degree. So the value of cos 90 degree again is 0. So it becomes E ds into 0, which gives us E ds equals to 0. Let this be equation number 5. So the value of top surface we have calculated for E dot ds for bottom surface we have calculated. So both the value is equals to 0. Now let's do the calculation for the curved surface. So for the curved surface, again we will do E dot ds is equals to E ds cos of theta, or E dot ds is equals to E ds cos of, let's find the angle theta between E and ds for the curved surface. So for that, at this point P, we will consider small area ds. So let's say this is area ds. So we need the angle between vector area ds and electric field E. So vector area ds, as I said, is always drawn perpendicular to that surface. So this gives us the area vector ds. The length of this arrow will give the magnitude and the arrow gives the direction. So that's why it becomes a vector term. Now at point P, the direction of the electric field will be going along the same direction as ds, because here we have given positive charge, and for positive charge electric field is always OB. So the direction of E will also be in the same direction here, which means that E and ds vector, they are going in the same direction along the same straight line. That means these two vectors are parallel to each other, and whenever the two vectors are parallel to each other, the angle between them is 0 degree. So therefore the value of theta here we will put it as 0 degree. So here you can write, since theta is equals to 0 degree. I hope I have made this clear why theta is 0 degree, because E and ds are in the same straight line going in the same direction, so they are parallel. Parallel vector means theta equals to 0 degree. So cos of 0 degree, the value is 1. So we have E dot ds is equals to E ds times 1. So we will put these values in this equation. So I am writing this here. So this gives us E dot ds is equals to E ds. Let this be our equation number 6. So what we have done till now is we have found out the value of E dot ds for the top surface, bottom surface and the curved surface. So we will put this value in equation number 3 now. So putting, which equations we are putting? Equation number 4, equation number 5 and equation number 6 in equation number 3. So when you put the value, on the left hand side we have integration of E dot ds. Now for the top surface and the bottom surface, the value of E dot ds is 0. So E dot ds 0, if you integrate you will get 0 itself. So no need to write the value for top surface and the bottom surface. So we will write the value only for curved surface, because for curved surface the value of E dot ds is not equal to 0. So we will have only integration curved surface, and the value of E dot ds we have obtained it as E ds. So here you have to be careful. Dot is between the two vectors here. So here we don't have any dot. Okay. So E dot ds vector is equals to, we are getting curved surface E ds only. So let this be equation number 7. So we have found out the value of this term, that is integration closed curve E dot ds is equals to integration curved surface E ds. Now we have this in equation number 2 as well. So we will put this value in equation number 2. So putting, which equation we are putting? We are putting equation number 7. In which equation? In equation number 2. So in equation number 2, if we put this value, then what do we get here? So in equation number 2, if you put this value on the left hand side, we will get integration curved E ds. On the right hand side we have lambda L divided by epsilon. So if you have not noted the equation, equation number 2 is like this: integration closed curve integration S E dot ds is equals to lambda L divided by epsilon naught. This was our equation number 2. So we are putting this value here. So instead of integration S E dot ds, what we are writing is integration curved E ds. So if you put this value here, we can get integration curved E ds equals to lambda L divided by epsilon naught. Right? So let me rub this here. So now, when we integrate, we have to see if we have two terms. If a term is constant, then that constant term is always kept outside the integration. So here we have E and ds. Now here ds can have any value. You can select the area of any value. But here E is a constant term, because E, as we know, is 1 by 4 pi epsilon naught q divided by r square. So if you don't change the distance, the charge is constant, this is constant. If you don't change the distance, then E will also be equals to constant here. So since we are finding out the electric field at this point P, the distance is not changing. So therefore E becomes a constant term. So E is a constant, ds is a variable. So we will take out constant outside the integration. So here, if you take out the constant outside, then we will have E integration curved surface ds is equals to lambda L divided by epsilon naught. So I hope this point is clear. Whenever you are integrating, if you have a constant term and a variable term, the constant has to be taken outside. And here electric field becomes constant because the distance is a constant term. So if the distance is constant, electric field becomes constant. So therefore we have taken out E outside the integration. Now our objective now will be to find the value of integration ds. Now integration simply means to add all the small equal things to get a larger thing. So here on the curved surface, if you add all ds, then what we will get is the curved surface area of this cylinder. So integration curved surface ds will give us the value for the formula for curved surface area of the cylinder is 2 pi rh. So here we will take 2 pi r, and the height of this cylinder, we have taken it as L. So instead of h, we will write it as L here. So here you can write down the formula curved surface area of cylinder is 2 pi r h. So instead of h, we are using it as L because we have taken the length of the cylinder as L. So integration curve ds will give us curved surface area of the cylinder, and the formula is 2 pi r h. So h is equals to L. So therefore we have written this term, right? So here, since this is in the product form, we can cancel this L with this L, and then we will do the cross multiplication. So E equals to 1 divided by 2 pi r lambda divided by epsilon naught. So we have cross multiplied this term, it goes to the denominator on the right hand side. Now let's rearrange this equation a bit. So E will be 1 by 2 pi, let's write epsilon naught here, and lambda divided by r. So this is the required equation for electric field at any point due to a long line of charge. Now we can also change this equation into something which we know, because we know the value for 1 by 4 pi epsilon naught, but we don't know the value for 1 by 2 pi epsilon naught. So let's convert this 1 by 2 pi epsilon naught into 1 by 4 pi epsilon naught. So for that we need to multiply and divide this by 2. So let's multiply and divide by 2. 1 by 2 pi epsilon naught, we have lambda divided by r. Now if you see in the numerator, so we have 2 into 1 into lambda, so this becomes 2 lambda. In the denominator we have 1 by 2 into 2 becomes 4. So 1 by 4 pi epsilon naught, 2 lambda divided by r. So this is another equation that we can use or we can derive. So this equation, especially we can use it for the numerical, because this value we know, 1 by 4 pi epsilon naught, we know the value. So if you have 1 by 4 pi epsilon naught, here we have 2 lambda, but if it is 1 by 2 pi epsilon naught, then here we will have only lambda. So this is the derivation that is very important for both ISC and CBSE. So I hope you have learned the derivation. Please do like, share and subscribe my video, and also share it with your friends so that they can take the benefit and they can learn from the videos. Thank you everyone.